So first of all, we quickly recap that in the previous video, we were able to factorize the series 1 plus 1 over 2 to the power of b plus 1 over 3 to the power of b and so on, which we expressed as zeta of b when b is greater than 1, which is when the series converges, as a product which involved the prime numbers. So the sequence 2, 3, 5, 7 and so on is the sequence of prime numbers. In this video, we will be making use of this factorization to give an analytic proof that there are infinitely many prime numbers. So before we come to the analytic proof, let us consider the elementary proof of Euclid that there are infinitely many prime numbers. This is a theorem that is proved by contradiction, so we assume that there are only finitely many prime numbers. So let us say there are n prime numbers, and let us denote them by p1, p2, all the way through pn. If we take the product of p1, p2 all the way through pn, and we add 1, we obtain a number which is divisible by none of the primes p1, p2, and so on through Pn. And what this means is that either this new number itself is a prime number, or it is divisible by a prime number which is not contained in our original list, and this is a contradiction. So in any case, we have shown that this is not the full list of prime numbers as we have assumed, so that there must be infinitely many prime numbers. And it is good to note that this number here need not always be prime. For example, if we carried out the first 5 cases, we would see that it does result in a prime, but 2 times 3 times 5 times 7 times 11 times 13 plus 1 is not prime because it can be expressed as 59 times 509. Very well, so that was the elementary proof that there are infinitely many prime numbers. So now we are going to give the analytic proof. And the idea is as follows. So if we could show that the series 1 over 2 plus 1 over 3 plus 1 over 5 and so on, which is the sum of the reciprocals of the primes, converges, then we wouldn't know whether or not there are infinitely many primes, because if there were finitely many primes, the sum would converge. But if it converges, it doesn't mean that there are finitely many primes. It could still mean that there are infinitely many, but the sum of the reciprocals converges. On the other hand, if we could show that this series diverges, then there is no way that there are only finitely many prime numbers, otherwise the sum would converge. So showing that this series diverges would imply that there are infinitely many prime numbers. And we are going to show that this series is divergent by making use of our factorization of zeta of b. And we proceed as follows. So first of all, let us consider our factorization. So the denominators here are the natural numbers, while the denominators on the right are the prime numbers. So let us take a logarithm on both sides. So we recall that zeta of b denotes this sum. And when we take logarithm on the right, we are able to write it as a sum. And now each of these logarithms can be unfolded as a power series as follows. And in each of these power series, let us take the first term and pull their sum outside the sum. So we have now this series, and in this series, we see that if we replace the 3s, 4s, and so on by 2s, then this series is less than this series where we have factored out factors of a half. And now we have a bunch of geometric series which we can sum as p is greater than 1. And when we do this, we find that this whole expression here is equal to this expression. So we have been summing the infinite geometric series. And we can simplify this expression. And this expression in turn is less than the expression where we remove these second factors in the denominators. And now this entire expression equals 3 over 2 times the sum of the reciprocal of the pth powers of the prime numbers. So we have shown that the logarithm of zeta of p is less than 1.5 times the sum of the reciprocals of the pth powers of the primes when p is greater than 1. And now we see, as we let p go to 1 from above, that since this expression diverges when p equals 1, therefore this expression must also diverge when p equals 1, as it is greater than this expression which diverges. This means that our series 1 over 2 plus 1 over 3 plus 1 over 5 and so on is divergent, and so there are infinitely many primes. So this concludes our analytic proof of the infinitude of primes. In the next video, we will be using this result that a log of zeta of p is less than 3 over 2 times the sum of the reciprocals of the pth powers of the primes to conjecture a result known as the prime number theorem, which gives an asymptotic formula for the number of primes up to a given positive integer. So it will only be a kind of conjecture, it won't be rigorous, but it will help us to conjecture the result, which very much later on in another playlist we are going to prove.